Hello and welcome to All Space Considered. I'm Dr. David Reitzel, and with me tonight is Laura May, and also we have our very special guest, Dr. Bob Pappalardo from JPL. And All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks, the City of LA, and we always like to thank our exclusive nonprofit partner, Griffith Observatory Foundation, that makes so many of our programs possible. Things like our school program and the equipment we use to bring you programs like All Space Considered. So thank you, Foundation, for all that you do. We have a wonderful show for you tonight. All Space Considered, we bring to you every third Thursday of the month. Well, every month we try and do it on the third Thursday. Every once in a while we shift it, so keep an eye on our website, because sometimes we have to shift it if there's something going on. But we've been pretty regular recently, and it's great. Today is Thursday, November 21st, and we are thrilled to bring you a show where we have a little news bulletin we're going to do up front. We have Vega's strangely smooth disk, Data Dig solves Uranus mystery, sonification of Earth's flipping field, meteorite sources found, and Ceres' center. Well, kinda. We'll talk about it. There's some questions we have about that. And then, of course, we're going to bring you Europa Clipper, exploring Jupiter's ocean world with our very special guest, Dr. Robert Pappalardo, who is a Europa mission scientist at JPL. So we are here to hear it from the source, essentially. I can't wait to hear about this. Now, this background image you're looking at, by the way, that you're seeing here, happens to be a double star. There's a white dwarf and there's a red giant making this crazy pattern. The red giant has swollen up where it's dumping material onto the surface of the white dwarf, and every once in a while enough piles up that the white dwarf goes nova. It explodes as a nova and brightens up, gets incredibly bright, and this material has been flung off in previous explosions that have happened. We don't know when this one's going to happen next, but there is one that we're waiting for. In the constellation of Corona Borealis, which is not up at night anymore, unfortunately, there is a star that is getting ready to go nova, and it could happen any day now. We're still waiting. So we'll tell you about it. We'll find maybe a space telescope to get a view of it, because it's off in the direction of the sun right now. It's not very viewable, but novas do happen, and that one's periodic. But there is something else that's going on that's been erupting. And Laura May, you've reported on this before.
Yeah.
And let's see if our live view, here it is.
This is just in time. Yeah, it's unbelievable. We have all these live cameras right now. This is in Iceland. So this is the 7th eruption of the Sunnukagagarathan system. And I don't want to get too excited about it because it has destroyed already. It destroyed, in fact, the parking lot of the Blue Lagoon this morning, a very famous tourist landmark. So, you know, they will have to see. So far, this eruption's been a little bit small. It's been a little bit smaller than the previous one, which lasted quite a while. The one thing that's interesting is that in the area, there are actually bombs left over from military bases. Oh, wow. And so I do want to encourage people who perhaps have seen some of the things I did there not to venture there if you're in Iceland. All that area is cordoned off, and it's near the power plant and things like that. But it's developing, and it's pretty incredible that now we get these webcams that just can, you know, immediately see what's happening. So yeah.
This is live. This isn't a video we clipped from before the show. This is a live stream happening now.
Yeah, so just about a day old.
Pretty crazy. The one thing to keep in mind, the Blue Lagoon there, the berms they installed to try and deflect the lava seem to be working. So the power plant itself and the Blue Lagoon so far are still safe. So fingers crossed.
In fact, they kind of plugged some of the holes on the berm this morning to protect the rest of the Blue Lagoon and the power plant. So hopefully that will hold up. And most of these eruptions on that system in particular have not lasted very long, a couple days. So hopefully that's the case. But we could be in for another decade of this or not. Hard to say.
Hard to say. But Earth is an active planet. We just need to keep that in mind.
Yep.
So. Another story, the Hubble Space Telescope and the James Webb Space Telescope were used together to study the star Vega. And you're looking at it here. Does everybody know where Vega is? There it is. It's in the constellation of Lyra. Let me see if I can get the laser pointer for our audience here. There it is. There's Vega, and Lyra's there. And it's one of the stars in the summer triangle. You can see the 3 stars. There's Deneb, Vega, and Altair. And they are still visible. This is a shot that I took from Stellarium About the time you'll exit the theater tonight. So around 8 p.m., 8:30, it'll look something like this. So if you want to go out and look to the west, this is the view you'll get. And Vega is the bright, whitish blue star. It looks sort of bluish white. We define it as white in astronomy in general. We give it a color as 0 in certain color bands that we do, which is funny. But it was discovered that there is a disk of material, a debris disk around Vega. And it was discovered by the Spitzer Space Telescope. This is a Spitzer image here. And those are just arc seconds. It's a measurement of angle up and down and left and right. But that disk you see around it is real. That's not just the starlight spread out because of the star. That's an actual disk around Vega, which was a little bit of a surprise, but it's a young star, a few 100 million years old. So it could be there. Maybe it hasn't formed planets yet, or they're in the process of forming. The Hubble Space Telescope, this is the image they created most recently. Now what they used was a coronagraph. They blocked out the light from the star in the center and then also subtracted off what they'd expect a point source to create, sort of the scattered light that would be left behind. And that's where you get all these strange streaks. That's where too much light was subtracted off. But nonetheless, that sort of circular feature you're seeing on there is real. And they're seeing the outer part of the disk. And it has material about the consistency of cigarette smoke, believe it or not, sort of very fine smoke particles in the outer part. The James Webb Space Telescope looked at the inner part, and it was incredibly smooth. So smooth, surprisingly so. They really thought they'd see some more gaps. They might thought they'd see maybe a planet forming down in there, the signs that a planet was disturbing this. And we don't see anything in there. When we compare the two, these are about to the same scale, side by side. You can see that the dip in here, this is real. That little dip is real in there, so something's probably causing that. And it corresponds to the dip in the inner part of the Hubble image in there. Now, if we zoom in, how big is this? Well, that's the black disk corresponds to Neptune's orbit. So the outer part of that is Neptune's orbit of our own solar system. So this is a pretty big disk, but not that much larger than the one that would have formed our own solar system. But if you zoom in a little bit, what's that in the middle? Let's take a look here. So yeah, smooth. So Santana smooth. Now, can we play this? No, there's no grooves in this. There's no grooves cut in there for us to drop the needle on and play this record and hear Santana. And scientists are confused. We think there must be planets, but there can't be one as big as Neptune. They have to be smaller if they're out there and they're in there, because Neptune would carve more rings. We would get grooves in here that we're not seeing. Now, we have seen other systems. On the right is Fomalhaut, and for a while we thought there was a B, a Fomalhaut B. No, turns out that it was a gas cloud that was dissipating and going away. Well, Webb was used to look at it as well, and you can see on the right-hand side how that disk is it has a ring in it on the right-hand side. We kind of see it on the left-hand side, but it's not nearly as well formed. So we're pretty darn certain there is a planet or more on the right-hand image. On the left-hand one, they haven't pieced it together yet. What's interesting is there is a bright spot in the very bottom center of the disk on the right-hand side. For a while, folks were thinking, could that be a cloud of gas? Could that be a planet forming? Well, we think it's a background galaxy. It turns out there's a galaxy right in that spot in the background, and it's probably what it is, but there'll be some more follow-up studies on this. But this surprisingly smooth disk, the Webb telescope, is revealing some very surprising things, because you'd expect maybe a planet to be piling up. Maybe they take a little longer to get going than we think. Maybe conditions weren't right. But there's more to be learned here for certain. So
yeah, in fact, we couldn't believe that it was a real disk. When we were discussing it in our meetings, we thought, oh, this is a computer-generated simulation, right? But no, it was the absolute smoothest. And all those particles, again, I think they're about the size of grains of sand that we're seeing, all sorting themselves, which is pretty remarkable. Yeah, the heaviest, the lightest particles have been blown away by the star, and the heavier particles are on the inner part. So it's been sort of self-sorting. Yeah, the disk is sorted. But no giant planets plowing through it. Which is very surprising. So we have another story with a outer planet on ours, one of our ice giants, as we like to call them. Laura May, what's going on with this here? Yeah, so this is a very famous image of Uranus, which was taken by the Voyager missions. Now, we've actually only ever sent one mission to Uranus. And it found something pretty remarkable. It found this obviously beautiful blue orb, not a lot of details on the surface, but most interestingly, there's been some new studies on the magnetic fields of Uranus, and at the time what we found was pretty odd. The magnetic field was quite small, much smaller than we would expect. We actually would expect Uranus to have the second largest magnetic field in the solar system. But again, we found this very small, quite compressed magnetic field. And this is actually what we think has happened, which is that at the time, interestingly enough, if you look at the year that it was visited, which I believe was 1986, you can measure this against the solar wind, right? Solar wind will shift throughout the solar cycle. We have an 11-year solar cycle or sunspot cycle of 11 years, and we'll get quite a lot of variations on the amount of solar wind. And it's interesting that Voyager was there during a solar minimum, right? And that is actually when we get a lot of solar wind. I know you might expect the opposite, but we get these very large corona holes that can stay quite stable for some amount of time. And that's why, interestingly enough, aurora chasing, if you want to aurora chase, you can either do it at maximum when we get very strong geomagnetic storms, or minimum is also somewhat of a good time because you get these large corona holes and that very stable solar wind. So we think that this is what was happening. We had a lot of solar wind and it was actually compressing all of that magnetic field. The plasma we were expecting to find in that magnetic field was not there. And so it's, this image looks so much like those kind of superhero battles where you have these kind of, they're all pushing their powers against each other. I don't know. It's a nice...
This is strange, but it's not Doctor Strange.
Exactly. So, and this may have an effect, by the way, on the moons. So we don't know if those moons are inert or not. And the revision of the magnetic field is rather interesting because it could point to having a little more activity on those moons, perhaps oceans, obviously. We will talk more about this, all those moons in the outer solar system. But again, they haven't been visited more than once. The decadal survey, in fact, came out, I think, a couple years ago, with a target to wanting to visit Uranus as a priority. We should definitely go there and get more data.
It's easier than Neptune, and yet they're sort of similar-ish. We could learn a lot about both by visiting. So we definitely need to go back. Here on Earth, some ESA decided to study our own magnetic field a little bit. And Earth's magnetic field every so often flips. Now, let's be very clear. We are not due for a flip. It is not going to happen right now. We're not expecting it to happen. We're talking about one that happened tens of thousands of years ago. So this is in the past. And they looked at the magnetic field and they said, well, when it flip does happen, the south becomes the north becomes the south. You can see here the south pole's on the top and that left-hand panel. The north is in the bottom. Then throughout it, they kind of get twisted up. You might have a couple of north poles that pop out, a couple of south poles, but then eventually the north will be at the top and the south is at the bottom, and then it'll be stable like that for tens of thousands of years, and then it could flip again. Well, they used satellite data. This is the SWARM constellation of satellites that actually can measure the magnetic field as it was laid down in the seabed. So the magnetic field can be sort of a memory of it, can be locked up as that magma cools down. The ocean floor is spreading, magma comes up, it cools down and locks in what the magnetic field was at that time. So they kind of could piece together a history of what it was like. People on Earth would go to locations and physically measure rocks, and they get locations where they've sampled it. So you can get a picture of the history of Earth's magnetic field. And they put together a little movie, and they put together a picture of what it was doing. And now here's the fun part. They decided to code the magnetic field with different sounds. Sounds of rocks cracking, sounds of timbers being stressed, sounds of dirt being poured. And each of those was pointed at a different part of this simulation you're going to see. So what you hear is what's known as a sonification of this data. So this is what they think the flip looked like, and you're going to hear these noises they've attributed to it. Now, is this what it really would sound like? No, they could have picked chirping birds and pipe organs and whatever to assign it to, but they chose these very sort of dark, ominous dark sounds. So let's make sure it's not too loud here. you can hear things happen when you see a magnetic field line spring into creation or one disappears. Now, I don't know if I'm learning anything from this or if I'm just creeped out, but we were amused enough we decided to bring it to you. So check it out if you want to watch the whole thing. It's about a minute long, and it was 42,000 years ago this happened. So I don't know, maybe we should choose kitten noises. Meowing. I don't know.
Immersive experiences at Griffith Observatory.
Exactly, immersive experiences. So reminds me of this Mercer Labs things I did in New York. Anyway.
But sonifications are interesting in the sense of there are some sonifications that are done also for Chandra, for example. Chandra's data has been sonified, and this is very useful also for low vision people to experience certain aspects of astronomy. So these are interesting. They're not just fanciful. There are ways to also experience astronomy without your eyes or with low vision. So they're interesting.
Yeah, Google sonification of NASA images, ESA images. They've done Hubble images. We've presented it before at All Space Considered. You might even find a video online where we talked about some of them before. Well, here at Griffith Observatory, we have a wonderful collection of meteorites. In fact, they're just outside the doors of our Leonard Nimoy Event Horizon Theater here. And if you notice this picture, there's something wrong with it. It's missing our El Segundo meteorite. We have a brand new sample out there. Make sure you take a look at it as you exit the theater tonight. It's a wonderful display, but I'm not showing you this. We don't want to talk too much about it other than I love talking about or showing this to point it out so people go look at it. What I want to talk about is the origin of meteorites. There are iron meteorites that are more metallic. There are ones that are a mixture. There are the palisades that have crystals of both iron and rock in them. And then there are ones that are more rocky, chondrites. And we've been able to trace the origins of some of these to the moon. When the moon has a big impact, some of those rocks that are thrown off can reach Earth as lunar meteorites. The asteroid Vesta, we've tracked some back to it. The asteroid Ceres, we've tracked it back to. So we've been able to track the origin of some, even to Mars, by the way. We have samples out on our edge of space right up there. You can go touch them. Well, but a lot were a mystery. Only a handful of % were really known where they came from. And most, we figured, had to come from the asteroid belt. That's where there are hundreds of thousands, if not millions, of objects out there of small sizes, and they bump into one another sometimes. And when they do, they'll create debris. And that debris can be knocked loose from its stable orbit out there and headed into the inner solar system where it can collide with Earth. So here's a couple of asteroids. This is Dactyl and Ida. Ida has a moon. The little moon is Dactyl. So even asteroids can have moons, which is cool. But they can collide, and when it happens, you send debris all over the place. Now, I like this one. It is a little fanciful, but you can see it looks like a trail is being created. And indeed, that sort of path and trail, the dust and the debris, it'll heat up by the sun. And as it spins, that heat has to go somewhere. It's given off, and that gives a little push. So these objects, depending on how they're spinning, will spread out into space. And we've learned that they'll spread out along a track like this, partially, but also they'll go inwards towards the sun. They'll go outwards away from the sun. And you can model this sort of information. And you can also measure the parameters of asteroids. So first of all, this inclination, this tilt. See how tilted up this orbit is compared to our orbit around the sun? Well, you can plot the tilt of an asteroid's orbit versus, and that's the vertical axis. This is sort of how tilted things are. And then right, left is how far from the sun. The ones on the left-hand side are 2 times the Earth's distance from the sun. The ones on the right-hand side are a little over 3.3 times the Earth's distance. And notice clumps show up in this diagram. And indeed, the names you see on here are the names of the major asteroids that are located there. So these things have had impacts. They've had other debris that travels along with them in space and is very similar. And if you take the length of that orbit, the semi-major axis, how long it is, how squishy sort of, well, it's not really the squishiness, but the length of it there, and plot that versus the distance, you can see they also clump up. So you can get an information about the clumpiness of them on here. Now, what they did is they took these objects and they worked them backwards. They did a computer model and they cranked time in reverse and said, where will these end up? And if you reverse time, was there a time these were all at the same location? Ignore the top for right now. It's just a crazy psychedelic thing they did, which I'll explain it a little bit. But that's their computer sample where they threw in a computer model and said, where will these things drift? So they were looking for that solar push. But the plot on the bottom is the important part. Notice, look at the green. It's kind of all over the place, and then it converges. So as we go back in time, going from left to right, you're looking back in time, it converges at a time a little less than 8 million years ago. And the 3 different models they did of this all converged at that same time. So it looks like there was some sort of collision that happened a little less than 8 million years ago. And believe it or not, when we date meteorites, there's a whole bunch of them that come from that time. So this is consistent. They've discovered that the source of many of the meteorites that fall come from 3 of these families. And let me find them here. It's the Kronos, Massalia, and Carene families. So those are the 3 that like 70% of the chondrites come from. These 3 little asteroids had collisions, and they were recent in the last handful of millions of years, so lots of debris is out there for us to sweep up. Now, does that mean there's not other debris out there? No, of course not. There are other ones that come from older falls, but as Earth sweeps up that debris, as it comes in and hits us, there's less and less of us to interact with. So it makes sense that these most recent collisions would be the source of most of the meteorite falls. So these chondrites that are super common came from these 3 families primarily. They still have work to do for about 5 or 10% of the origin of meteorites, and they think if they go deeper and look at fainter asteroid families, they'll be able to figure it out. So the work they did on this is extensive. They simulated a lot of collisions. They simulated a lot of data to prove their systems were consistent, were self-consistent. And I was fairly impressed with the work. So, yeah, and you can hold a meteorite, by the way, right here at Griffith Observatory. We have chunks you can hang on to right at our edge of space. So our final little news story we wanted to talk about is about Ceres.
Yeah, so Ceres, many people are upset about the demotion of Pluto. I like to say promotion personally, but Ceres was also demoted a very long time ago, or rather it was reclassified quite a few times. It was an asteroid, and well, first it was a planet, then it was an asteroid, now it's a dwarf planet, and it lives between Mars and Jupiter. In fact, it is the OG asteroid, as we would call it. It was the first asteroid that was found by an Italian astronomer. And amusingly, we talk a lot about how Uranus was almost called Planet George. Well, Ceres was almost called Planet Ferdinand in honor of the, at the time, regent. So fortunately for us, we stuck with the nomenclature of naming of all of these. But Ceres is pretty interesting. It was visited, so this is a size comparison, by the way, just to show you. Ceres, in fact, holds about 1/3 of the mass of the asteroid belt, so it's pretty large. It is larger than all these other asteroids. Those are the other large ones. We've got Pallas, Vesta, but it is not that large if you compare it to Pluto, for example, right? Interesting comparison of sizes. So Pluto is about its surface size, if you unfurl it, it's about the size of Russia. So Pluto is really quite small. And then, of course, Ceres is even smaller. But we actually visited Ceres. It is not insignificant. So this is an artist's image of the Dawn spacecraft, which was there around, I think, 2015, around that time. And
ion drive on it. It started over at Vesta and then used its ion drive to
That's right.
cruise
visited
over.
several targets. So this is an image, one of the images from the Dawn mission. You might notice it's such an unusual image. It's got this little white spot right in the middle. It's got a couple of other white spots on it, and I picked this image because you might be wondering, what is it? You know, it looks like the moon, it looks like Mercury, but it's actually composed of a lot of clay, right? So comparable to this lovely little clay activity. But we were able to get a lot of details from the surface. And so this is an image of Ahuna Mons. This is a mountain on it. Similarly to, in fact, the moon also has mountains on it. And Ahuna Mons is about 6,000 meters tall, or about 4 miles, I believe. Perhaps a sign of former cryovolcanism. And this is one of the things that was investigated. So all these little white spots, so you can in fact see Ahuna Mons right there on the bottom of that image. It is that very large, that very tall structure. It looks quite small, like a little bump. But you can see those white spots on there, and those have continued to kind of puzzle planetary scientists while we try to figure out exactly what they were. So this is an image, I believe it's Okator Crater. Okay, I wasn't sure how to pronounce it. Okator Crater. Of all these little white spots on there. So potentially, they may be salts, water that has sublimated. There are a variety of interpretations. Because we think potentially, so here's another image inside the crater of these white spots, but we think, this is a study that just came out of Purdue, that Ceres may have also been a little bit of an ocean world. So we're right on topic with all these moons, Uranus's moon potentially, and Ceres, and it's pretty exciting. So part of the changes, or why this is kind of new information, is that we thought that the surface sublayer of ice might have been around 30%, but now we think it might be as high as 90% ice, which is pretty impressive. And this was found partly through what we call crater relaxation. So there's a lot of studying of craters, the way they evolve. And so if you have your little asteroid with a lot of ice, but you have a little bit of rock in that ice, that changes quite dramatically how these structures, how the surface will form, how the craters will move. And so it may have had this kind of muddy ocean underneath the crust. And so we have now this leftover ice, and it needs more investigation, I think. This is definitely a place we should go. So we were discussing which images to use to show you the interior, and I brought up, should I find a labeled one because it's clear? But again, it's kind of like all these bodies, this is what all these missions are trying to figure out. We want to know what the insides are made of because that tells us about habitability, that tells us about whether there was potentially life possible on there. So this is another image that is, has indications for potentially having this rocky inner core and then this kind of ocean. So we have different interpretations, and this is a comparison to some of our other moons, leading us into Europa. Smoothly from Ceres, a little further out.
Yeah, a little further out. To end with this one, this is okay, where did it go? This was a movie here. Let's see if I can get it to play.
It's also, by the way, a very close, accessible, icy world, and that's one of the advantages, why we should revisit it.
Yeah, so this was a movie that the Dawn spacecraft released. The team released it that shows a rotation movie, a full rotation of Ceres, and you'll see these various features we're seeing, but it's a rich world. It really is. These are worlds we're looking at, and Ceres is classified as a dwarf planet, just like Pluto is. It's a small one, but you can see it's squished itself into a roundish shape, and it's not orbiting a larger object as a moon. So I think it's quite a beautiful object. The colors have been a little enhanced there, but it's a very, very interesting object. So. But on to Europa. The OG ocean world, absolutely. But let's all welcome our guest. Welcome to All Space Considered, Ron. Thank you so much for joining us. And how long ago was the Europa Clipper mission first thought up? When did this start?
It depends on how you set the date. Let's see. NASA formalized the mission, gave it the green light in 2015. So that's when we, had to go. The NASA had a competition to select the instruments. Said, okay, now JPL, make this work. And we launched about 5 weeks ago. But it was 1998 that I joined my first science definition team to define the science for a possible future Europa mission.
Wow. Yeah, we had you on the show in 2018. So that was only 2 decades after, I guess, you'd started coming up with the instruments. But I know you have some slides to show here, so if we want to switch over to Bob's. Oh, wait, we get to do this down here. Let's see,
okay.
Stage computer to,
All
there
right.
it goes.
Well, let's go right to the fun stuff. This happened. Let's see. Hold on. Let's make this work.
There we go.
We got sound? Sound's out?
Yep.
All right.
Live at NASA's Kennedy Space Center for NASA's Europa Clipper mission, a nearly 2 billion mile, 5.5 journey to Jupiter's icy ocean moon.
And liftoff. Liftoff of Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Side booster separation confirmed.
Fairing is separated, and those will be recovered by SpaceX's own recovery ship, Go Cosmos.
This is a big moment for the program, for NASA, APL, and JPL. Let's watch.
Europa Clipper, separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon Europa. And what a sight.
And now they wait for acquisition of signal.
And I believe we have it. Right. There it is. Confirmation of signal from the spacecraft Europa Clipper.
In theaters soon.
Stay tuned. That's
What
right.
Also, everything that preceded the launch, right? With the hurricane, tornadoes, and
So much, right? It's like our spacecraft didn't want to leave the Earth. Yes, it was scheduled for the 10th of October, the launch of Europa Clipper, and the end of the prior week, the regular reviews, and we're gearing up, and folks are arriving at the Cape. And then we got a little worried, at one of the weather briefings, there might be some rain coming next week. And then over the weekend, there's a chance of a hurricane. And this thing, exploded into
as it
a
did,
very serious hurricane in the Gulf, and hit the west coast of Florida, and was over the Cape at essentially the time we were supposed to have been launching.
Yep.
But of course, by then we had
How long was
had
the
to
launch
postpone.
window? How much time did you actually have?
About a month.
Okay.
Yeah, we could have gone into the first week in November if need be. But of course, you don't want to risk the possibility of a large delay if you don't make that launch window.
Yeah. Now, the launch we just saw, that was with the Falcon Heavy, and they threw away those boosters. SpaceX
Yes.
likes to land
Yes.
those back, but
We
you
wanted
needed every bit of thrust.
We wanted to squeeze out every ounce of juice
Okay.
in those side boosters. Yep.
Yeah. So
And but they did capture the fairing there. But that's to get us on our way to first a gravity assist with Mars.
okay.
About 3.5 months from now, March 1st. And then we'll come back around for a gravity assist with Earth in December of 2026.
Will you
and
turn
then
on
out
any
to
of the
Jupiter.
cameras when you pass Mars?
Yeah, I
and
was
Earth?
wondering if there's any data acquisition
Funny you ask.
happening.
So, our thermal instrument, which will look for hot spots on Europa and will also tell us temperatures in order to derive the surface properties, the roughness, which will help with a future lander for sure, but to understand the properties of the surface. It needs a calibration, and so by flying by Mars, this kind of instrument, a heritage instrument, Themis at Mars, has characterized that surface very well. So we're going to do a calibration to make sure the correction that we need to apply is right. So about a day out, Mars will be about 70 pixels across. So we'll get a thermal image in 3 colors of Mars' surface. And we'll also do an end-to-end test of the radar. Europa Clipper has an ice-penetrating radar. So at Europa, we're going to shine long wavelength radar at Europa's ice. And ice is pretty transparent to long wavelength radars, but water is not. So if there's water in the shallow subsurface, or maybe we'll even get to the ocean, it'll bounce off the ocean back to the spacecraft where we can detect it. So it's pretty tough to test a huge radar system that is actually mounted to the solar arrays of our spacecraft, here on Earth at JPL or at Kennedy. So we're going to do an end-to-end test at Mars, which again has been characterized by radar before. Otherwise, we'd have to wait till we're in the Jupiter system and test it out at Ganymede. We'd like to know things are working.
And this is the first time that the outer solar system has had that kind of radar, right?
Absolutely.
Yeah.
Right. So the opportunity for discovery is huge.
Now, how are all the systems on the ground?
Everything is working wonderfully well. We deployed the magnetometer boom, and we deployed the radar. Here's my little Europa Clipper spacecraft model. So I mentioned the antennas for the radar are on the solar arrays. They're 2 high-frequency radars and 4 very high-frequency radar antennas. And sticking out the back, the little tail of the spacecraft there is the magnetometer boom. And it has on it 3 magnetometer sensors. That way we can understand the gradient, what the effects of the spacecraft itself are, to be able to subtract that out. So it's really the most distant one that's most sensitive to the environment at Jupiter and Europa. So that boom deployed successfully, and the radar antennas have deployed successfully.
So
we're done with deployments.
Oh, so the stressful deployments are...
Except for
primary.
covers on a few instruments.
Well, amazing.
Yeah.
That's exciting.
Slowly but surely.
Especially since, well, we all know what happened with the Galileo mission, getting to Jupiter, losing the
Right.
high gain antenna.
Right.
The data rate, the ability to transfer all that data was dropped dramatically.
Right. We
So-
have no antenna deployment here.
Yeah.
So we were all holding our breath when the solar rays deployed. Well, okay, it was a long deployment. We couldn't really hold our breath that long. But we were very happy when those solar arrays appropriately deployed for that 100 square meters of area, which, we don't need that much in the inner solar system, but when we get out to Jupiter and Europa, we need...
So now what is expected at Europa? What do you think it will be like, and what instruments were put on the craft to study Europa?
Well, let me talk about Europa a little
Yeah.
bit. Let me show Europa up here, similar to the image you show. This is a global mosaic of images from the Galileo spacecraft, the same spacecraft that took that picture of Ida and Dactyl. Europa is about the size of Earth's moon, but very unlike Earth's moon, right? Earth's moon's covered with craters. Europa, you can see a few roundish spots. Some of them are craters and some of them are not. From the number of large craters, we think we can estimate the age of the surface, the average age, as about 60 million years. So since the time that dinosaurs roamed the Earth, something has repaved Europa. It's probably a geologically active world, and we're pretty sure there's an ocean down there below the ice. How thick is the ice is a big question, maybe 20 kilometers or so. It's tidal heating, it's squeezing as Europa orbits Jupiter that maintains this liquid water ocean. And of course, we want to do things like confirm, is the ocean really there, right? We're pretty sure there's an ocean, we'd like to know better. And we can do that with the magnetometer and with the radar that we've talked about. We want to understand how active is Europa. So thermal instrument, are there hot spots? Are there plumes at Europa, as suggested by some Hubble and other telescopic observations? So we have an ultraviolet spectrograph, which is our plume hunter.
Now, in this image, for folks that aren't familiar with it, what are these reddish-orange stripes we're seeing?
Let me zoom in a little bit. Europa is crisscrossed by these ridges and grooves. So the bright areas are icier, and we don't really understand how these ridges and grooves form. There are ideas, but there's like half a dozen ideas. Is it compression? Is it extension? Is it warm ice pushing its way up? Is it sliding of ice plates back and forth past each other to warm the ice, and then it rises up? So we're not really sure, but it's a sign of some sort of activity, and maybe water is involved. And then there are the darker, blotchier areas, and those are aptly named chaos terrain, where it looks like the surface has kind of been cooked from below. There's been some heat source that has disrupted the surface. And notice wherever the surface is disrupted, there's this dark reddish stuff. The color is exaggerated here a bit, but it would look kind of an ochre color to the eye. And we're not sure what that dark stuff is, but it seems to be coming from the interior. It might be salts. Salts aren't dark or reddish or ochre, but some salts, like table salt, actually darkens to that color in response to being irradiated, charged particles hitting it. And Europa is bathed in Jupiter's very powerful magnetic field, slammed by these charged particles, and so maybe it's table salt that has come from the interior of Europa and been exposed at the surface and then darkened. So we want to find that out.
So we'll have pink Himalayan salt and ochre Europa salts.
It's new businesses.
Yeah.
And
Could
we
it
want,
be a mix? I mean, of these sulfur and...
Yeah, and sulfuric acid hydrate's been suggested, Epsom salt's been suggested, magnesium sulfate hydrate. And we want to know if there are organics in there, of course. Are there organic materials from the building blocks of life? Because everywhere on Earth, there's water. Essentially everywhere, there's life.
I think a lot of people wonder also why we haven't sampled this. Obviously, it's very difficult, right, to sample. And this is a habitability mission, not a life or sampling. But
well, in a sense, we'll be sampling. That is, we're going to be flying sometimes as low as 25 kilometers off the deck of Europa. And why that low? Because if there are plumes, or if there are just, well, we know there are micrometeorites hitting Europa and knocking stuff off the surface. We're going to sample the dust with a dust analyzer on board. Those dust particles will hit it and vaporize, and from that material we'll be able to say, oh look, there's signs of organics here. We also have an extremely sensitive gas mass spectrometer. You don't think of Europa as having an atmosphere, but it does. It's a picobar, 10 to the minus 12 of Earth's atmosphere. And so we'll fly by and through that very thin atmosphere, capture it, ionize it, bounce it back and forth in this meter-long tube to separate the ions based on mass and analyze what is that material.
Was there any of, I know that we sampled some of the plumes on Enceladus, for example. Were any lessons derived from this on how to build the instrument for what we might eventually, if we can sample these plumes?
Yeah, absolutely.
In Enceladus, they saw salts, in fact, is my memory.
And signs of, organics, simple organics and more complex organics. So this is a much more sophisticated instrument that can with much better mass resolution and mass range than even the Cassini instrument. And if there are plumes at Europa and we can fly through them, or even if we can't fly through them because stuff spreads around, then that will be just wonderful in telling the composition of the interior of Europa.
Yeah. Now, we're interested in this because this is a candidate world for life, if anybody out there hasn't clued into this yet. Sometimes we don't want to say these things and get people too excited about it, because this isn't necessarily going to say, yes, there's life there, but it's going to tell us a lot about, is it really habitable? Is there an ocean there that could support life?
Yeah.
Now, what are the reasons we think Europa is a good candidate for life? Why Europa?
Here's a cross-section of Europa, right? As I mentioned, wherever there's water, there's life on Earth, but there are other ingredients that are critical. So we talked about organics. What we need is to know if there are the right ingredients for life, the right elements, chemical elements that could build organic materials. Maybe there are organic materials. And then we need to know if there is the right chemical energy that could support life. Right? Life is like a little battery. We need the positive and the negative. If they can get together, then those chemical reactions could potentially fuel metabolism, power metabolism. So we need to understand what the chemistry is, and we also need to understand, can stuff from the surface, where we're pretty sure there are oxidants, oxygen-rich material, but oxidants, can they get into the surface, through the ice shell, into the ocean, where they could potentially react with reductants, the other half of the chemical battery, that we expect at the interface between the ocean and the seafloor. Because, well, if there are warm areas, like on Earth's seafloor, there could be, the water could be charged with chemical nutrients, with reductants. But even if the water is just reacting with rock, that's enough to make hydrogen-rich material reductants. And there are lots of places on Earth where instead of life being powered by photosynthesis, it's powered by chemosynthesis. And we're not talking about photosynthetic organisms at Europa. We're talking about, could there be chemosynthetic organisms?
Early Earth had methanogens that were living off of methane that was there. And in fact, the oxygen-rich environment killed them off. They couldn't live in there. So there could be a whole different type of life in Europa living on what's available there, but we just don't know.
Right. Again, we're not a life search mission, but we're trying to understand what's the, does Europa have these ingredients for life? And then in the future, potentially, we could put a lander on the surface, dig down below the layer that's processed by the charged particles, right, from Jupiter that destroy organics, dig down in some of this reddish stuff and sample it, put it in a mass spectrometer and say, are there signs of life there?
Yeah. Now, one important thing is the water does interface directly with the rock, we think, on Europa, that the ocean goes all the way down to that rock. So it's ice, liquid, then rock.
Yeah.
Other moons, we think it's ice, water, ice, and that's not as favorable.
Right. When the moon is bigger, like Ganymede, Callisto, Titan, then the H2O layer is thick enough that the pressure forms high density ices. Ice 3, Ice 5, Ice 6. Yes, Vonnegut fans, there is an Ice 9, but not in icy satellites. It would be even higher pressure than that.
I was reading that also there may be some convection. So some of the ice may be convecting those, in fact, those cycloidal ridges. And that's something we don't really find on Earth, the potential for that difference, I guess, in heat, or that ice convecting up.
Yeah, this picture shows things called diapirs, right? And on Earth, there are salt diapirs. Salt rises up through sediments, like in the Gulf of Mexico or off the coast of Germany. Here, it may be warm ice that's rising up through cold ice. So this is a lot like what goes on in the rocky mantle of the Earth, where warm rock rises up through cold rock. And so this may be another way for the ice shell to circulate, to bring stuff up from the base of the ice shell to the surface, and surface materials down, the cold ice sinking down. And yes, this doesn't happen in Greenland or Antarctica because they're not thick enough.
Right.
But here we have, once the ice shell is 15 or 20 or 25 kilometers thick, it should start to convect.
Okay. Yeah, I know that on Pluto, the heart that there could be a convecting body of some sort. At least it seems to have signs of that.
Or there may be cells of nitrogen convection.
Yeah, things like that going on. So all these icy worlds have weird things that we don't see here on Earth.
Right.
What on Europa are you most interested in seeing results from that's coming from Europa Clipper? What are you just waiting for?
Let me show you the chaos terrain, right? Apnea, as we talked about. Chaos terrain. So yeah, here on the right there is about the closest image the Galileo spacecraft got of Europa. That's about 9 meters per pixel. Right? You look at that, and it starts to look like a place you might visit in Utah and Arizona, right?
Yeah.
Right, an arid environment of the Earth, a Monument Valley. And you can see that same block on the left where the surface has been kind of broken up. So that's a place where the surface has been mobile. These plates have moved apart, crumbled in place. There may be water down there. I didn't talk about the scale. I guess there's a little scale bar there, but there you go.
That's great.
One way that it's been proposed chaos terrain might form is if there is a lake down there in the subsurface, or was a lake in the subsurface. And if the subsurface ice melted, like in response to convection, which might concentrate tidal heating, well, then the volume changes. You go to smaller volume and going from ice to water. So what happens then? The surface collapses. So maybe chaos terrain is a sign of a place where there have been or are lakes in the subsurface.
Okay.
So that could be a very exciting place to explore with Europa Clipper's radar, with the thermal instrument, with super high resolution imaging, with compositional data. Right? We also have infrared spectrometer to look for the chemical signatures, stuff there. Oh, and the camera, we have 2 cameras, wide angle camera for understanding the broad swaths of the surface, and a narrow angle camera, which from 50 kilometers altitude will get us 0.5 meter per pixel images. Wow. So can't wait to see the chaotic terrain close up, because that could be a kind of oasis, if you like, that if we find there's liquid water and signs of organics and heat, maybe it's a source of plumes, then that's the kind of place we might want to go back with a lander in the future.
Yeah.
And there have been quite a few missions to Jupiter, obviously. Recently we have Juno that's still there. You mentioned the Galileo mission, which got a lot of the data that I'm guessing many things were based off of. There is another mission that is en route there that was launched last year by European Space Agency called JUICE, the Jupiter Icy Moons Explorer. And I'm curious if there's any chances of collaboration. So I think I remember that in December 2000, in fact, there is somewhat of a collaboration between Cassini was en route to Saturn and passed by Jupiter, and there was a collaboration on the magnetic data with Galileo. Yeah. Is something similar going to be done maybe with JUICE there?
We are talking regularly with the JUICE folks, roughly monthly. We have a video con with the leadership of the science leadership for the JUICE mission. And that partnership goes way back because we used the JUICE mission arose from conversations of, hey, what might the U.S. NASA and what might Europe ESA do together in the Jupiter system? And scientists dreamed up the idea of two spacecraft, one that concentrates on Europa and another that concentrates on its neighbor Ganymede. And what science could we do jointly in the system together before that, as we're both orbiting Jupiter? That envisioned an orbiter at Europa that evolved into what became the Europa Clipper with multiple flybys, and the JUICE mission came to be and is on its way and will explore the Jupiter system and end up in orbit around Ganymede.
You have a faster path there. You're going to arrive first, I think.
Yeah, larger rockets, so we actually pass them on the way out. But we're coordinating informally. Yeah. It's a grassroots effort to say, hey, we have a committee, essentially, about 20 folks who have been talking about here's the science that we might be able to do together on the way, mostly magnetosphere, heliophysics, science, solar wind. And then when we get to Jupiter, there are so many possibilities. So we're trying to understand what are the highest science priorities and what could we do without tweaking the missions too much. We don't want to make our mission more expensive, more complicated, but we do want to maximize the science. Let me give you an example or two. We have the same family of ultraviolet spectrographs. So imagine looking at Europa from two different perspectives at the same time to get stereo of the glowing atmosphere, right? And then we'll be orbiting Jupiter and making many flybys of Europa while the JUICE mission is in orbit around Ganymede, and Ganymede has a magnetosphere of its own. So the JUICE mission will be sensing the effects of Jupiter's magnetosphere on Ganymede's magnetosphere, and then we can be measuring Jupiter's magnetosphere, and then it just takes communication of what's going on. And we're already saying, hey, there's some cool opportunities on the way out there. Let's see if we can coordinate.
Because that seems to be one of the difficulties is, at least for Galileo, was seemingly separating what was Jupiter's magnetic field and what was potentially Europa's induced magnetic field, I'm guessing. Yeah. And will this help clarify?
And it's even harder with Ganymede because Ganymede, we think, has an induced magnetic field as well and an intrinsic magnetic field. Wow. So it's really tough to tease out that induced field. Yeah. So this may help. Yeah.
Well, does anybody in our audience here have any questions? We want to open up to you too. We've been sitting here chatting. So far, no. Okay. Well, let me look and see if our YouTube audience has any. I did say to text me if they had any questions. So let's see if I've gotten any.
What are some results that you personally are the most excited about? You originally, or you come from the world of geology, and this seems like it's a geologist's dream. Just to, I mean, everything from the chaos terrain to there's just so much going on just on the surface without even the prospect of life or oceans. Those surfaces are so interesting.
Well, let me just some almost random pictures. I just clicked on one of Europa's surface, and that image on the left, right, showing a band. You're talking about seafloor spreading on Earth. The same kind of thing may have happened in ice on Europa. Well, that image is probably about 200 meters per pixel from Galileo. We have 10 to 15% of the surface covered at that resolution. And that's what you need to map these things, to understand what's going on. So what I'm personally excited about, as closest to my research, is we're going to have over 90% of Europa mapped so that we can understand, is the region here tied to the tectonics and what happened in the region over here, right?
Yeah.
So then we can start to put together a global story.
Yeah.
What we can do now is put together regional stories, but we want to know from the pattern of ridges and grooves and bands, what does that say about the history of Europa? How did it rotate? How did it move? Did it undergo polar wander or what we call non-synchronous rotation? We mentioned cycloidal features. We want to understand how they're mapped globally, and that'll help us understand how they form.
I'm very excited to compare these Galileo images to the new ones and look for differences between them, because there could be, slip strike faults if these are faults, and you can see motion along them. In fact, you can trace some of these lines, and then there is a shift, so they look like faults on them. But more data separated by time will tell us more.
That's right. Yep. We actually don't know how active Europa is today compared to how active Europa was 60 million years ago. Yeah. It could be that it's in a steady state, it's just as active today as it was then. Or it could be Europa went through this burst of activity 60 million years ago and now it's kind of quiescent. There are reasons to think it may be a cyclical activity. So again, piecing this together will help us understand it.
And there's about 50 flybys planned, is that correct?
Yep.
Is there any chance of potential readjustments if, for example, the ice-penetrating radar finds a particularly interesting spot? Will anything be readjusted to have another look at it?
Yeah, it's possible. Here's the spirograph of our flybys, because we want to cover the whole moon, by orbiting Europa, by orbiting Jupiter, making flybys of Europa, we're trying to see all angles. Here, let me show you this cool rotation movie.
Wow.
All right, this is showing some of the flybys. It's an old trajectory, but it's very similar. Star Trek fans, I like to think of the Tholian web here.
Yeah, our YouTube audience did have a question. They wanted to know, is there a chance you're going to crash into Europa? Because some of these look awfully close.
Yeah, they are awfully close. But the navigators at JPL are just awesome and put together these trajectories. And we don't go in and immediately do a 25-kilometer flyby, but using the Enceladus example with Cassini, right? We started farther away and then moved closer and closer. And the warmer colors here, of course, imply closer flybys. So you can see the flybys are concentrated on the sub and anti-Jovian longitudes. So that's what we have to do with a mission that's orbiting Jupiter, or to make sure you're not crashing. Because if you're going into the leading or trailing points, well, you'd be going through Europa or coming out the other side.
Now, are you going to look at anything else at Jupiter? Do you have any other moons that you're going to take a little peek at as you go by?
Well, we're going to do a full-up test of how we do an encounter by using Ganymede as an example, and we'll do that sooner. Here, let me flip back to this one because I don't remember the dates, but I just put this on here. Help me remember. So Jupiter orbit insertion is April of 2030, and then the Ganymede Science Encounter demo is October of 2030, and then the first Europa flyby in March of 31.
Yeah, and there's 9 Callisto flybys I see there too. So there'll be some other work on there.
So we're not planning on those being science flybys, but it's an opportunity for calibration. And again, as we talk to the JUICE folks, for example, to understand the interior of Callisto, wouldn't it be wonderful if we can add our understanding of the gravity field of Callisto to JUICE's understanding? And we're going to be measuring, the Doppler as we fly by Callisto, so it's kind of free to be able to learn more about Callisto at the same time.
And so much of this data will also go towards the next mission that will, I presume, is this already in the works, the next mission, or is this something that will start being planned once we actually arrive at Jupiter?
There have been concepts for a lander. It's hard to land on Europa because it's an airless body. You have to take a lot of fuel with you. And but there are ways to make it work, but it's also difficult in terms of radiation because you're sitting there on the surface, and a person would get a lethal dose on the surface of Europa in minutes to hours. So the spacecraft has to be quite radiation hardened, as the Europa Clipper is, and so a lander, the current concepts would last about a month, So can we get the science back that we need in a month, right? And for the price it would probably cost. So I'm sure there'll be additional studies, and I sure hope to see that we see a lander in our lifetimes.
Yeah. Now, before we wrap up here, we have a couple of audience questions, but I wanted to ask you, what's the little panel you have there that's on our easel?
First, let me show you this cool picture.
And then we'll do a couple of audience questions.
So, here, let me put the picture up as I talk about this a little bit. So this one's encased in acrylic. The one on the spacecraft is not, of course. This is what we call our vault plate, but the folks who assembled the spacecraft call it the poem plate, and you'll see why in just a second. We know about the Voyager Golden Record. We know about the Pioneer plaque. Lots of spacecraft have carried symbols and words with them. Now, the Voyager and Pioneer plaques and plate, well, those are kind of emissaries to the stars, right? Maybe they will be found someday by another civilization. Our spacecraft won't. It's going to crash on Ganymede, most likely, is where we'll send it. We can't crash on Europa because of planetary protection. So we derived a message kind of to ourselves. One side of the plate has in it the words for water in 104 different languages, 103 of them encoded as sound waves, and in representative languages of the Earth. You can hear them spoken on our Europa Clipper website. The central one is the American Sign Language symbol for water as represented through a Fourier transform. And then the other side,
as one does.
As one does. On the other side is why it's called the poem plate, because we wanted a message from the Earth to ourselves. Many missions, Mars missions, for example, you can sign up to send your name. And we did that, but we didn't want to just have folks send their name. We wanted them to co-sign a message. And that message, thank goodness she said yes, came from the poet laureate of the United States, Ada Limon, and her poem In Praise of Mystery, a poem for Europa. And I recommend you go to YouTube and look it up and hear Ada Limon read the poem for Europa. It's just beautiful. So we also have that chip with over 2.6 million names encoded. All the people who signed up, your name's on there. My cat's names are on there. And they're not encoded in the chip. They're etched on the chip. And this is a duplicate. If we had a microscope powerful enough, you would see the names etched on this chip here. We have a portrait of Ron Greeley, who was really fundamental in getting this mission going. When we were talking to the Europeans back in 2007, 2008, dreaming up these mission concepts, he led the science definition, or co-chaired the science definition team. Oh, and by the way, that chip, see, it's in a little bottle, because it's our message in a bottle, and that bottle's in the center of the Galilean satellite system. And we also have the Drake equation, because Europa Clipper will help us to understand toward understanding a couple of the terms of the Drake equation. So the audience is invited to come down and have a look later on.
So we had a couple of questions, and then finish up. Yeah, here.
Okay.
Yeah.
I know this is not a life-seeking mission, but I'm not getting any younger, and I want to know. And so my two questions are: first, is there any information this mission will come back with that will lead us to a high likelihood of some possibility of life inside? And secondly, how hard would it be for flying plumes to just see if there's a cell swimming around?
Yeah.
You know?
Yeah.
Yeah. So let me.
Is that planned?
I want to repeat the question for the YouTube audience in case they couldn't hear. First question was, well, could we pick up a cell if we flew through it? Was one of the questions, and the other was, what are you going to learn about the likelihood for life?
Right.
Are there any measurements that'll make us more hopeful? Let's say.
It's a harder one, or maybe they're related questions. So again, understanding if there are organics at Europa that are native to Europa, I think will be really key. If we find evidence of shallow liquid water, I think that would be key. If there are, so there are a lot of ifs here. If there are plumes at Europa, it's a very hard measurement to make, so we're not sure if there are. And if those plumes tap ocean water, which is another hard thing to do, because cracks on Enceladus can go much deeper than cracks on Europa can go because of the gravity. But then if those two things are true, then we could tell something about the nature of the ocean water itself, as we think we are understanding from Cassini at Enceladus. Then if we found organics, we could say, hey, these are coming from the ocean. That would be a big deal. The odds are very low, but if Europa's ocean were teeming with life and plumes are real and they tap down to ocean water, not impossible, but I think it's very, very unlikely that we could measure cells, but it's not impossible, right? It's just a very low probability. So I don't want to get people's hopes up. But I think much more likely we'll find evidence of the ingredients of life, maybe someplace like one of those chaos areas that's an oasis that we can explore in the future. But yeah, it's multi-generational. I don't expect to be around when we ultimately send cryobots down through Europa's ice and explore that ocean, which people are researching and working on. It could happen, but maybe it's 50 or 100 years off.
Any other final questions? Over here, yeah.
On the note of the approach plans, you mentioned a lot of them were relative to Jupiter. Are any of them relative to planetary features we've already spotted, like specific bands, large areas of chaos, like any distinctive features?
Sure. Here, let me go to this map. You can't really tell the map unless you have Europa memorized. Well, here. We just happen to have a Europa right here. Fans of Annie Hall maybe know my joke. Okay. So, yes, there are lots of features. We're not specifically targeting features, but as the trajectory evolved, right, we iterated between the tour designers and the science team. And the science team would say, hey, one of those trajectory ground tracks passes near Thrace and Thera Macula. Can we shove that over just a little bit so that we go over them? And tour designers look at it and say, sure, it'll cost a little bit of propellant, but it's worth doing that. And those are dark chaos zones. That'll be fascinating to go over. One of them we looked at earlier. There's Agenor Linea. It's a very unusual bright band on the surface, down in the southern hemisphere there. And we made sure that the trajectory goes over there. So there's been iteration with the tour designers. You see a few names in blue on the map where we looked at, could we go over those features? There are a couple of large impact structures, so we're going to go over one of those, Callanish. So yes, not specifically driving the trajectory, but these little tweaks have helped us get to a lot of fascinating places where we can test existing hypotheses, but there'll be lots of discovery as well.
Well, fantastic. Well, thank you so much for joining us tonight.
You bet.
It's been a pleasure. Let's thank our guests. We'll have to have you back in October 2030 when you do the first test. So we'll
be happy to.
But very exciting mission on the way. I was very excited when Europa Clipper was picked, and it's successfully on the way there. We just have a little bit of a wait, and that's how it goes. So thank you so much, everybody, for joining us at All Space Considered. We'll see you next month, of course. And as always, All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks, the City of Los Angeles. And we like to thank our exclusive nonprofit partner, Griffith Observatory Foundation. Thank you, everybody.